When I first joined the Air Force, of course all I could think about was planes. But as I studied more, I learned that aircraft could be made more fuel efficient through composite material.
Composite material is a material formed of two or more materials that are physically and chemically different. Such material consists of a stiff, strong material referred to as the reinforcement, which is then surrounded by a separate material called the matrix. The reinforcement is used to support the structure, while the matrix provides orientation for the reinforcement. Composites cannot be confused with alloys. Alloys has to contain at least one metal. Due to the various different components in alloys can be either homogeneous or heterogeneous, but composites can only be heterogeneous. For example, air is a homogeneous mixture consisting of molecular combinations of nitrogen, argon, oxygen, carbon dioxide, and a ton of other stuff. However, heterogeneous means that the composition varies from place to place and the materials are separated from each other. The most commonly used composites for aerospace applications are aramid fiber reinforced polymers, which is also known as Kevlar, the stuff that policemen use so that they don't die when they get shot. But lightweight composites can reduce the empty weight of an aircraft by about 16%. The reduced weight is partly achieved by tailoring the orientation of the reinforcement to align with the highest stresses in the structure. Lightweight composites can reduce up to 25% of fuel emission and could improve global fuel emissions by 12% by saving 73 million tons of carbon dioxide emissions per year. So to compare the fuel efficiency of composites versus metals in terms of mechanical property, we can see that composites density is 40% lower than steel, and aluminum, which makes it the lighter material of the three. We can also compare isotropic versus anisotropic. Metals are isotropic, so this means that they will compress or stretch the same way no matter which direction you push or squeeze for them. Oppositely, composites are anisotropic, so this means that they will compress or stretch depending on where you apply the force. An engineer can control where the composite structure has the greatest stiffness and the greatest strength wherever the greatest tension or the greatest force is applied. The orientation saves weight where the least force is applied and puts the most weight where the most force is applied. This saves a lot of energy in aerospace structures. We can also compare the differences in fatigue between metals and composites. Fatigue is when metals fail due to high stress and strain after multiple loads. Metals, like I said before, are homogeneous, so that means once a crack starts, it will easily spread throughout the entire structure. Luckily, composites are heterogeneous, so once a crack starts, it can be contained before spreading throughout the material. This fatigue resistance, in addition to corrosion resistance, makes for high durability in the aircraft. All in all, composites have many advantages for the aerospace industry. Features of composites are its lightweight, its high stiffness, high strength, and high durability. Composite material can improve the mechanics of an aircraft by decreasing weight and increasing fuel efficiency. Composites are now being increasingly integrated into the commercial airline industry in aircraft such as the 787 Dreamliner and the Airbus A380. So the next time you get on a plane, look at the name and the manufacturer and see if you're traveling on a more fuel efficient aircraft, and have a safe trip and fun travels.